My name's Alex Miller. Thanks everybody for coming. I'm going to talk about Clojure today, and I'm going to talk about abstraction more generally. Just as a very brief way of intro, I'm from St. Louis. I've been doing Clojure for a little over a year at a team of 7 people, so I have a fair amount of real experience using Clojure. I've worked in a bunch of different languages over the years. I've worked in Java for over a decade and did some pretty detailed stuff, bytecode mangling and concurrency and more advanced topics. I'm also the creator of the Strange Loop conference in St. Louis. And so what I want to talk about today is really about, I think, abstraction. This is really in two bullet points why I wanted to do this talk. I think abstraction is really what we do as programmers. It's why we're here. And I think that I've found that Clojure is a really good language for creating abstractions. So that means that I think, therefore, I think Clojure is a really good way to do programming. I don't think it's the only way to do programming. I like lots of different languages. So what is abstraction? I looked at lots of different definitions out on the web and Wikipedia and whatever. And while I found ones that I think were more complete, this one I think actually captured, this definition eliminated the irrelevant and amplified the essential. So this is the abstraction of the definition of abstraction. But I really like this one. I think that really gets at the essence of being able to look at a bunch of things in our programming language or in our program and pull out the thing that's common between all of them and let the rest of it fall away. And use that to make our programs better and clearer and more concise. So here's another well-known programming expert, Stephen Wright, in his quote about abstraction. I put this up there because it's funny, but also because it's actually remarkably close to what we do in our daily life as programmers. Is that we're not building things and constructing things. It's all in our heads pretty much, and writing a little bit of code to back it up, but. We're basing our lives on these towers of abstraction, from all the way from binary machine code and zeros and ones and operating systems and virtual machines and low-level languages and high-level languages and virtual machines and libraries for ORM and things like that. So we're living in this world of abstractions, and I would like to think that means that abstraction is really important. So. Clojure, very briefly, before we get into it, is a Lisp dialect on the JVM. So Lisp was created in 1900 BC or something like that. It was a long time ago. And it's dynamically typed. It's always compiled. There is no Clojure interpreter. So that's a question that comes up a lot. It dynamically compiles to Java bytecode and runs it on the Java virtual machine. I did mention a little type there. There is actually a CLR port of it. It's incomplete and behind and not generally what anybody uses, but it does exist, and other people have taken stabs at actually implementing it on JavaScript VMs and things like that. Those are all should be considered esoteric for the moment, maybe in the future. So I want to start talking. This is not a Clojure tutorial, so my goal is not to teach you Clojure, although if you happen to learn some along the way, I'll be happy about that. I do want to talk a little bit at the beginning here about the basics of the language, just so we have some clue what we're looking at. I go to the Structured Interpretation of Computer Programs as one of the best books ever written about programming from my perspective. And they break this down as the way to start understanding a language is really primitives, means of combination, and means of abstraction. So if we look at the primitives, these are some of the Clojure primitives, and I don't have everything on here, but this is enough to get started. I think some of the numbers and strings should be pretty obvious how we're doing that. Symbols and keywords may be less familiar to you. Symbols are basically a way to identify something, and they have both a namespace, which in this case is math, but that can be a dotted thing over there, and they roughly correspond to like Java packages or something like that. And then it also has a name, which in this case is fib. And a symbol is used to identify something, to name something. And so it typically refers to something else. A keyword is actually also a symbol. It also has a namespace, although it's often not there. So this is an unnamespaced keyword. Keywords are a special kind of symbol because they actually always refer to themselves. So that means if you use a keyword in one part of your program and somebody else uses a keyword in another part, those always are going to be identical. And I say that word very carefully. They're not just equal or equivalent. They actually are identical in the language and forevermore. So they are very idiomatically used as keys in a map or ways to sort of identify parts of a data structure. And we'll see those as we go through. So means of combination. I've taken some primitives here, 2 and 3. I want to then use some primitive operation plus, and obviously I want to add these things together. You do that by creating an expression, putting them in parentheses, and I then want to evaluate this expression by first evaluating the first argument, evaluating the second argument, and the third argument here, and then I'm going to invoke the result of the first argument in this list. And you now know how to write Lisp. So that's I've taught you the syntax of Lisp. There are a few other special cases, which we'll get to a few of them later. You'll notice that this is prefix notation, so the operator goes first. Many people find that troublesome. I do not. I've stopped even seeing it, other than a few cases where you do things like greater than is really awkward to write in a prefix notation, but you just get used to it. Because, well, I'll get into that later, but there are libraries that actually use infix notation for some things, and that is actually possible to do in some limited cases. So the means of abstraction. So over there on the right, we've got an expression that's the same expression, a very similar expression to the one we just looked at. Now we want to know how can I take that thing and use it and reuse it. So I've actually wrapped that into an anonymous function. So this is the syntax for an anonymous function. You've got this special operator at the beginning, fn, and it's going to take one argument named x. So I could put multiple arguments in there if I wanted. And then it's going to evaluate, when you evaluate this function, it will evaluate the expression inside the function. And that's great, but that's an anonymous function, so I have no way to refer to this thing. I can create it and use it any place that I need to use a function. But if you want to name it, then you have to put that inside. You have to use def to define a variable named or identified by square, which is a symbol. And then on the right side, you've got actually the definition of the function. So this is the way you can define a variable that contains a function. Since you do that all the time, there's actually some syntax sugar for that. This is just a macro that wraps up this form. So you've got defin is the way that you idiomatically the way that you define a function. And you'll see that it's basically the same. We've just removed some of the syntax characters in there. So that's our first abstraction that we're going to talk about, which is functions. Functions are themselves an abstraction. So let's look at an example of what I mean by that. Here I've got a square. So square is a function that takes an x and does times xx. We've got cube, which takes an x and does times xxx. There is superficially some similarity here, right? We're taking a number and multiplying it some number of times. So I've defined an exponentiation function now that says take an x and multiply it n times, some x to the n, right? And I can then, the simplest way to write this is to use this function repeat, which repeats x n times, and then apply that to the multiplication function. So I've abstracted these two things into a function. There are other ways you could write the exponentiation function. This is a recursive way to write it using cases. It sort of expands into something like that at the bottom as you implement it. This is a tail recursive version of it. I'm not going through all the syntax of this. It's not important. The important point is that I am abstracted from what the function does by the signature of the function and its symbol. So that, to me, this is a black box. I don't know as a user of this function what's actually happening underneath it. And the fact that I can let the details of the implementation fall away is where we get abstraction out of this. So switching from functions over to data for a little bit, one of the key things about Clojure is that it has a really rich set of data structures. And there's not a lot of them, but there is a very carefully chosen core set of them, and they are used everywhere for everything. And that's actually really, really important. So these four you'll see everywhere in Clojure. Lists are obviously sort of a linked list type data structure, and they're implemented very similar to how you would implement a linked list anywhere else. Vectors are indexed index fixed size structures, so they're kind of like arrays in Java, or an array list in Java, maybe is a better analogy. We have sets that have this notation with the hash brace, and sets, of course, don't have any duplicates, and they're not necessarily ordered, so there's some other constraints there. And then maps at the bottom, you'll see, in this case, I'm using keywords as keys. So the keys here are A, B, and C. And when you use the literal map constructor, you just alternate keys and values. If you want, you can put commas in there to separate them. Commas are treated as white space in Clojure, so if they help you to understand your code, then you should use them. At the REPL, when it prints out maps, it will print them with commas just to help you see where the breaks are between them. And that's it. That's really the key set. There are also queues, but there is not a literal constructor syntax for them, and they're not used quite as much. So the key thing here is that when we go back to if you thought back to our primitives that we talked about at the beginning, things like 5 and ABC, those kind of things are very clearly values. They're immutable, unchanging values. Your 5 is not going to later on become a 2. It is a 5. And what's not obvious is that all of these are also actually values. They are unchanging, unchangeable, immutable data structures. And that's really important for a lot of the other parts of the language, and we'll start to see that. And the key thing here is that some other thread can't assimilate your data, so you don't want to do that. I had to get one Star Trek joke in there. And so the way that this is made efficient is that when you modify a data structure, you get back a new data structure. Naively, you would actually copy the entire data structure, right? That's obviously far too slow to actually work in practice. So what actually happens is called structural sharing, and all what are known as persistent functional data structures use structural sharing to efficiently manage multiple instances of the data structure. And the linked list is really the easiest way to see this. So I started here with a list A, 1, 2, and 3. And there's a little quote character up there. That's just a thing that helps me construct a literal list. And then with B, I'm actually taking A, and I'm going to construct, cons, a new list with 4 at the beginning. And you notice when I did that, I didn't actually create a new list, 1, 2, and 3. I just reused the one that was there and put something at the beginning that pointed into the old list. And similarly, if I take the rest of A, which we'll get into what some of these are a little bit later, we take the all but the first item, and we add a new front item onto it, we can similarly just construct pointers into other parts of the list. In a language where you had mutable data structures, this would be chaos because some other thread or somebody else could go along and change that change that 2 to a 4, right? And if they did that, then your data structure is broken. But because all of the data structures are immutable, that's not possible. So it's perfectly safe to point into subsets of the old data structure and be able to reuse those. And I guess before I go on with that, I should mention that I've given the example here with linked list, but there's actually a lot of very clever stuff that's done to make vectors and maps and sets all actually share this property as well. And it's outside the scope of this talk to talk about how that's done, but it's pretty fascinating. And so when we think about what all collections share in common, the one thing that you can pull out of it is that they all have sequential traversal over values. And in Clojure, this is called a seq. In Lisp, you really have this key data structure as a list, and everything is kind of done with lists in Lisp, and you have this very rich library of things that work over lists. Unfortunately, those don't extend to other data types because there weren't really other data types at the beginning. So what Rich Hickey, the creator of Clojure, has done is sort of lift this abstraction of sequential iteration over a data structure into this thing called a seq, and that means that everything can use it. Seqs are kind of similar to iterators, and I totally stole this slide from a Rich Hickey talk because it was really good. He was really comparing here the differences between something like a Java iterator or a C# enumerator to a Clojure seq. And the key here is that there's really three sort of operations on the left that you want to do as you're iterating through a structure. One is to know whether there is something more. One is to get the first value. And one is to sort of get to the next value. And in Java and in C#, both of those collapse two of those operations into one. And those are problematic. So in the Clojure seq, you've actually sort of pulled those different operations out, so there actually are three iterations. Some other problems, I don't really know the C# code at all, so I'm not going to talk about that. But in Java, like one of the other big problems with iterators is that they have state, and they're working over collections that also have state, and that both of the state in both those cases is mutable. So if you read, like if you get a synchronized iterator over a synchronized, or if you get an iterator over a synchronized collection, that iterator can only be used if you're also synchronizing on the original collection. So there's lots of caveats in the Java doc if you go read that stuff. And if you don't do it, then your program is not thread safe anymore, and bad things can happen. In Clojure, the seqs are immutable data structures. So they're views, they're sort of immutable logical list views over the original collection. Because the seqs are immutable and the collections are immutable, you're not going to get any problem with thread safety or anything like that. You can very safely sort of shuffle these data structures all over the place, and it's no big deal. And I wanted to kind of I think I said most of the things I wanted to say here already, but the key thing on the left here, I'm really listing some different possibilities of what a vector could look like. So it can be, you could have nil, or you could have an empty vector, or you could have a vector with some data items in it. And when you call seq on a vector, you're going to get back, on an empty or a nil one, you're going to get back nil. It's going to say there are no more items here. And in the case of when you actually do have items, you'll get back a seq. For first, and it should be obvious what I'm doing here. So you get back the first and the rest. So you'll see that this is actually a really powerful abstraction, this idea of being able to have sequential traversal. It's supported not just on all the core collections, but a string is seekable that will turn it into a sequence of characters. Java collections are seekable, so you can walk through Java collections. Java iterators and enumerators are seekable, and there is some work being done behind the scenes to deal with the mutability issues there. JDBC result sets are seekable. So you can think of a JDBC result set as a sequence of rows that you're walking through, each of which is a map, which is a sequence of column values. Trees made up of a vector that contains other vectors. Those can be thought of as a sequence. You can traverse a sequence through the tree in like depth first order, for example. XML is a subcase of trees. So these are actually all functions built into Clojure Core. So there's an XML seq function in Clojure Core that can give you a sequence of all the nodes in an XML tree. You can walk through all the lines of a file, files in a directory. You'll see that once you start thinking this way, you tend to see it a lot. One of the other benefits is that because it's a sequential traversing, you're only going an item at a time, is that you don't actually have to calculate all of the sequence. And so Clojure, it's perfectly normal, actually, to deal with infinite sequences. So here I've got this iterate function. Iterate is a function that will repeatedly apply a function. So we see inc is a function which is a function to increment a value. So it's basically +1. So this will apply inc to 1 and get 2, and then it will repeatedly apply inc over and over again. So you get 2, 3, 4, 5, 6, 7, 8, 9, 10. And actually, you get all the way to infinity. So the result of iterate inc 1 is actually a lazy infinite sequence. if you want to get something out of that, I can use something like take. I can take some things out of it. So it's very idiomatic in a language that supports lazy sequences. Haskell would be another perfect example of it. To instead of like writing a program to compute the first n primes, instead you write a program to compute a sequence of all primes, and then you just take the ones off that you need. That's a sort of a very typical way someone would write that program. So there's a rich collection of functions, or a rich set of functions on collections and sequences. I've sort of broken these down here. The key thing on this slide is that these 4 major data structure types share common traits. So the little things on the corners are common traits in the underlying Java code that Clojure is written in that actually support the different data structures. So things like all of these data structures are both counted, which is why there's a count function in the middle, and seekable, which means that you can get a sequence off of them. And a few of them are also sequential. So a list actually is a seq. It's actually, the seq is the list itself in that case. And you'll see that both vector and map are associative. And that means that they map from a key to a value. In maps, that's obvious what that means. In a vector, the key is actually the index of a value in the vector, or in the array, if you want to think of it that way. So these functions, once you understand this, the functions, you can sort of guess which functions will apply to different things because they're sort of broken up by trait. Some quick examples of how to use these data structures and functions. We saw the quote form before. Cons, as we also have seen, as a way to construct lists. First and rest are the sequence functions, so we can get the first thing in a list and the rest of the list. We can count it. We can walk through and get the nth value in it. There's lots of other functions here as well. Vectors, the idiomatic way to add something to a vector is conj. There are other ways to do that. And I've mentioned that vectors are associative, so you can do things like get with a collection and a key. In this case, the key is 3, which is actually the index into W, which will return you 4, because 4 was added to the end of that. Maps. So maps are used all over the place as well. We've created one here. Assoc is how you actually add something new to a map. There's also a dissoc to remove a key from a map. And assoc can actually take multiple key value pairs, so you can put a bunch of them in there if you want. There's also a merge and a merge with that lets you put maps together. Keys and vowels let you get to the keys and the values. You'll notice when I do this that they don't necessarily come out in any order that corresponds to the construction order. You're basically it's dependent on the hash values and things like that. There is a way to get a sorted map if you need to do that. And then here at the bottom, I actually have 3 different ways to get something out of the map. The first one is probably the most obvious. It's a get function on a map that takes a key and it returns the value. The second one, in this case, you'll see that the map itself is in the function position. And that's because the code that implements map actually also implements the function interface. And that means that the map is a function, because maps are functions of their keys to their values. So this is actually evaluating the map as a function and passing it a key and getting back the value. Perhaps even more common than that in actual Clojure code is to instead pass the key first. Keys are actually also functions. When you give them an associative data structure, they look themselves up as the key and return the value. So these 3 are all basically equivalent. You actually see the last one most commonly, and we'll see that later on in some examples. So I wanted to make sure that was clear. So we talked about the seq abstraction. This is some of the seq functions that are out there. This is an incomplete list. And there are other libraries, optional libraries in addition to this, that provide more functions. So we're not going to go through all those. The point is there's a lot of them. And if you think back to that big list of all the different kinds of sequences I talked about, that means you can use these functions on things like database result sets, XML, files, directories, lines in a file, whatever you want to, anything that is sequential. That's really powerful to have this rich set of functions that you can use everywhere. So you get this common set of data structures, and you get this common set of functions, and most Clojure code is made up of that core. So these are some examples of sequence functions. And so range gives you a range from 0 to whatever by default. So it's giving you a numerical range. There's other options for that. Filter, probably the three most important ones here are filter, map, and reduce. So if you saw Jim Dewey's talk this morning on Clojure, he talked a lot about common functions that you see in functional programming. You saw all of those, I think. So filter is applying a function odd to the range produced by 6, which is what I had in the first line there. So it's just filtering out all of the ones that are odd there. If you look at like map, it's going to apply the increment function to a range of things and add 1 to each of them. If you see reduce, is going to reduce a sequence down into one value by applying the function over and over again. These are really powerful. Here I'm using numbers here for all these because it's really concise. I can make pretty examples that way. But you use this because these are all working on sequences. You use these all over the place. You might take a sequence of database rows that are coming out of the database result set and map them to transform each record that comes out and then reduce them to like add something over them or do something like that. So you're going to do that with these rich data structures that you build up. And once you get used to doing that, it can be very powerful to do some pretty high abstraction things. I wanted to give one more example of a higher order function. Those three functions that I mentioned before, filter, map, and reduce, you'll notice all three of those actually take a function. So odd is a function, inc is a function, and plus is a function. So those are, in functional programming, those are anything that takes a function or returns a function is usually called a higher order function. And that's sort of getting to the notion of functions as first-class citizens in your language. So as an example here, I created a function on the right that takes a y and multiplies x's times y. So you'll notice that the x is actually coming from outside that expression. In this case, we're actually closing over. So this is a closure. You're closing over the environment and actually capturing that sort of that free variable there. That's going to return to when you call it with a number 10, I get back a function named x10 here that when you give it a number, it returns 10 times that number. So I'm actually created a function that returns a function. And then I can invoke it down here. I'm using map, so I'm actually passing that function as a higher order function over a range and multiplying that times 10 or whatever. So this is nice, based on a pretty famous post by Steve Yegge, which was about 7,000 pages long. It's a fun read, but he tends to be lengthy. And the basic gist here is that in Java, sort of verbs or methods are owned by the class that they're in. Everything has to be in a class. So you have to create a class to wrap up any piece of functionality. And in functional languages like Clojure, they're really sort of first-class citizens. You don't treat, one's not owned by the other or anything like that. You tend to use them both equally, on an equal footing. Before I go any further, are there any questions? Yeah.
With those comments, can you slide back or like use a slash?
This right here?
Yeah.
So this is so the Clojure uses a thing called the REPL, the read eval print loop. So here I'm actually typing this at the REPL, and this is what it's printing back to me. And what it's printing to me is the Clojure's understanding of sort of representation of the thing I just created, which was mult. This is actually a reader syntax for a variable with that symbol naming it. So it's just telling me I made a variable, and that's what it's called. So, is it clear? So moving forward, data types. So you might say, well, yeah, in my, it's great to have all these functions, these little pieces of, these little functions that I can call over the place. But when I write OO programs, I write classes, right? I create a person that's got some things in it. And how do I do that same kind of thing? I have, those things naturally show up all the time in programming, right? Where we've got a bunch of data values that apply to the same thing, and we want to carry them around together. It's certainly possible to just do that by creating a map in Clojure. And really, your first choice in Clojure is always to use a Clojure data structure. And that's sort of part of the power of the language, is that these core data structures are so can cover almost anything that you need to do. So here I just created a map that actually has a key, or 3 keys, which are first, last, and iColor, and said what they were. And at the end, I'm using that keyword syntax to actually extract the last name out of the map. So I'm just using that map. And that will work great, but we don't really know what that map is, right? It doesn't have a type associated with it. If we wanted to, we could put a key in there that was called type, and then we could use that to identify what that is. And that would be perfectly fine. And in some cases, that makes sense to do something like that. Clojure also has the structure called a record. And a record is basically satisfying these same goals as above, except that it also wraps up this common set of this set of well-known fields and names that thing as person. So that actually lets us make a thing that is a person. And then when we define an instance of variable, we'll just say, this is actually a Java interop syntax to construct a Java object. So if you wanted to create a date, you'd say date dot, or you could say new date would be another way to do it. And I've passed the 3 fields that match up to the 3 well-known fields in the record. And then I use it in exactly the same way, because records actually implement the map contracts and actually are maps in every important sense. They just also have this type associated with them. So why would it be useful to have a type? It would be useful if you want to do something like polymorphism, right? So one of the big benefits we get in OO is that we have these objects that are that have behavior that varies based on type. So we can say something. We can have an interface that a bunch of different classes implement, and they all have a relax method, for example. And when we call relax on some object, we don't have to tell it that it's a programmer object or a normal person object. It just knows how to figure out, it knows how to find the right method to actually run at that point. So it knows how to dispatch and find the actual function that we're going to run. And there are actually 2 built-in ways in Clojure to do this. It's pretty easy because of all the other functionality in Clojure to actually build your own if you need to. But these 2 actually suffice for virtually everything you would need to do. The sort of older way to do this is called multi-methods. The other one, which we'll talk about next, is called protocols. Multi-methods have a lot more features, but protocols have 1 or 2 extra features. Or they have fewer features, but slightly different features, and they're also a little faster. So there's just trade-offs in which one you use, and I use both regularly. So here I've created we saw it before, programmer and normal person. Programmer has a favorite language, and normal person has some activity that's not programming. I don't know why they would have that, but I'm not one of those people. So I've created those at the beginning, and I should note that if you're used to using Java, this is actually generating a Java class under the hood that has all of the fields that you specified, and a constructor, and a valid equals, and a hash code, and a toString, and all of the map functions to do other things and stuff like that. So this is actually equivalent to about 50 or 100 lines of Java code. This is one of the examples of how Clojure gets very concise compared to Java code. And def_multi is actually defining a function that will be polymorphic. And here I have another function that we can apply to actually tell us how to dispatch to the right instance of a function. If I want to get the same sort of behavior that I was talking about on the last slide, where you choose based on the type of the object, you want to take the class of the thing that's coming in and dispatch based on that. And this is by far and away the most common function to use as a dispatch function. But we'll see in the next slide that it's not the only function you could use here. This really has to be a function that takes the number of arguments that you want to take to your multi-method, and by default it's 1. So this is expecting to get 1 argument, which is an object. We will take the class of it, and we will dispatch based on the type. So the 2 different possibilities we have here are defined with def method. They use the same name of the function. That's how we find that they're associated. And then we've got one for programmer. It takes that 1 argument that we talked about, and it says, I'm writing whatever. And here I'm using that keyword syntax again to pull out the language. And in this one, normal person, we say, I'm doing whatever. So as an example, we say, for Clojure, I'm writing Clojure, or I'm taking a walk. So that works great. If we then go to the next one here, I've actually used a different function. I actually used, I mentioned before, keywords are functions. So I've actually used a keyword here as a function. It will look up that key in the thing you pass it. So a record actually has, a language key in it. So that's oh, actually, I did this wrong, didn't I? Oh, yeah, I did it right. So a programmer record has a language key in it. It's going to look up that key and then choose based on the string, Clojure or Java, what to do. So here I'm actually dispatching not on a class or a type. I'm actually dispatching on a string literal. And you can make that function do whatever you want. If you want to look at, if you get past 3 arguments, you want to look at all of them and the types of all of them and dynamically pick some value which chooses a multi-method, that's perfectly fine to do. So there are lots of sort of more advanced uses of multi-methods. You might also notice that this doesn't really actually require that this be a record here. If it actually is just assuming that there is an associative data structure it can be passed that might have a key named language. So you can pass it a normal map as well, and that will work, or some other data structure that you create that would have that function in it. Some other features that multi-methods have are that you can define a default place to go, so sort of like method missing in Ruby. You can actually, if you're using class, there's some special features. It will actually understand Java hierarchies, and it will dispatch to the most specific match to your particular object that gets passed in. You can define your own hierarchy. So you can define an ad hoc hierarchy on keywords or whatever types you want to define, multiple hierarchies, and actually tell it which hierarchy to use. There are possibilities when you start doing this to get collisions where there are multiple possible matches for something, especially if one of those is added later. Like, you don't actually have to define all these in one place. You can define a multi-method, define one method for your data structure, but I could let someone else can come along later and define their own implementation of that method. That's perfectly fine. It will dispatch. It'll dynamically find that and dispatch to it. You may find that there's collisions in that case, and you can resolve that with preferences that tell you, in the case of a collision, prefer this type over another type. If you want, you can get yourself in trouble doing this, but it really covers. I have not run into a case where I wasn't able to do what I needed to do with it. So another feature we have here is called protocols. And so protocols, I've sort of done a little bit different example. Protocols actually let you define not just one function, but actually multiple functions that are sort of bound together. And you might be tempted to think of this as an interface. And that's not a bad way to start thinking about it. It's actually it's subtly and important and different and important. It's different in important ways, but not ways that we're going to go into today. But you can think of this as 2 functions, teach and read, that are going to exist on this teacher protocol. And you say then that I want to extend the type programmer to this interface, this protocol teacher. And I'm going to provide implementations of those functions. And then when I call it, I just say teach, and I pass it an instance of programmer, and it will find, oh, that's right, there's a programmer. I defined that he implemented this protocol that had this method, and it will dispatch to the right one. Protocols, you notice there is no dispatch function here. You have to dispatch based on type. That's not that it cuts off that option for you. The benefits you get out of it are that you can do these multiple things and sort of collect them together under the same group. That's useful from a just understanding program sort of point of view. The other thing is that it's actually creating Java interfaces and things under the hood that leverage more of the underlying Java machinery, and it means they're faster. So that's the other. It dispatches much more directly, I should say. So that's another big benefit. So moving on, as we've talked about polymorphism, now we're talking about state. So we talked before a lot about immutable data. And immutable data is great. Hopefully I convinced you that immutable data is good stuff. I could do another whole concurrency talk about why immutable data is good things. But the next question is, how do I maintain state? I mean, my data is changing, right? I might have more than one thread that wants to look at the same piece of data. And I might have two pieces of data that I need to sort of change together, right? So there is actually a whole model of state inside Clojure. And I'd say that concurrency is really one of the strongest suits for Clojure. It has a very well thought out concurrency model, state model. And it's really designed to work in multi-threaded and multi-core environments. And that's really one of its biggest strengths. So Rich calls this the epochal model of time. That comes out of some philosophy stuff, which I'm not going to talk about. There are some presentations you can find on the web that are great that you should go watch. The basic idea here is that every time I have, is that we want to separate the identity. So something like checking might be a variable that I have that holds the value of my checking account, right? And that checking account is just an identity. It's just a thing that points to some value at every point in time. So the value is not changing. That value 120 the value is 120. I then apply a function that will modify that value, that will use that value as an input and return the new output value. So these are pure functions. Jim used that term earlier today at the functional programming talk. It's sort of a function that doesn't have side effects, basically. And those pure functions take you from one immutable state value to another immutable state value to another immutable state value. And time is sort of modeled as this progression of immutable values. When you want to go reference it, you reference it through this identity, right? Those things are sort of more bound up together in languages like Java. You'll note that it's very useful to be able to, you often will have more than one variable that you need to change together. You might have a checking account. You might also have a savings account. And there's a constraint that those two things can't go below a certain value, right? So in that case, you actually have not just this one timeline. You might have another timeline for savings account. And when you need to apply one of these functions, you actually need to involve two of those. And at that point, the timelines need to come together. And that is done in Clojure with software transactional memory. So there are a number of languages out there that are using software transactional memory in some degree. Haskell has one, and there are ones for Java that you can get. There's one called Multiverse. It's been sort of a research topic for a long time, and the implementation in Clojure is somewhat different than other ones that are out there. It's a little special in some of the choices it made. One of the really important choices is that at any given time, we expect to be able to read the value without messing with the timeline. Because we've got this series of value changes, at any time, a reader can come in and read the current value. It doesn't have to lock to do that. You might not see the one that's changing at the newest time. You might see an older version of it. If you really need to see the latest version of it, then you need to actually use STM to be involved in some sort of a transaction that puts those things together. But if you don't need to be, I'll just get the value, and that's okay if it's not the newest value, that actually comes up a lot that you want to do that. So at any time, you can dereference the value. And there's really three constructs here that Clojure provides, and I'm not going to go, this is another whole talk to talk about this. But the three constructs are atoms, which are kind of like atomic classes if you've ever used Java util, concurrent, atomic type stuff. They're really designed for uncoordinated synchronous change. They don't participate in the STM. You can't coordinate the change of that with some other value. But they do give you an identity that two different threads can look at or that you can pass around and that you can change. Refs are the main construct that we'll use to deal with change. And they're going to allow you to coordinate changes from across multiple different refs at the same time. And the STM is used to coordinate those changes. And the final one is agents. And agents actually sort of model time as a series of functions that are a series of messages that are being applied to it. So there are some similarities to actors, if you're familiar with actors from Scala or Erlang or other languages. They're not active, they're not sitting in an active loop waiting for things. They're implemented a little bit differently. And the state of that agent is always available. So like actors, the state is internal. It's not visible. If you want to know what state it has, you have to send it a message, and it will tell you what the state is. Agents, you can always dereference them, and get the value. So they're just a little bit different in how they're oriented. So I'm going to move out of the state model and talk about macros a little bit. Has everybody used a language with macros? Anyone? Okay. So macros are what a lot of people mention as like one of those things that's hard to get in other languages. And that's because macros really lets you abstract syntax. So that's a very powerful thing to say. There are other languages that let you do things like this and create new syntax on the fly. Imperative languages like Java or C or C++ or something like that don't do this, and the syntax of the language is very rigid. Things like LINQ actually are starting to give you some of this capability back into imperative languages, which is why I think those are pretty interesting. Groovy actually has the ability to let you modify the AST of your language at runtime, so there's some interesting things that can happen there. Here, this is actually the code from Clojure core that implements AND. AND is not a function. It's not a special form of any kind. It's just a macro. And the thing is with AND that you don't actually want to implement all of the or evaluate all of the arguments in the AND eagerly, because you might not need to evaluate all those arguments. So you want to defer evaluation on some of those arguments. And so the way this is implemented here, if AND gets an empty seq, really, it's going to say true. If it gets X, it's going to return X, and every value has some logical truthiness to it. So you'll get whatever the truthiness is of the first thing in there. So if it's anything other than nil or false, it will evaluate to true, logical true. If there's more than one, then what it's going to do is you'll notice there's this little backtick here. That actually puts us into this. I'm actually writing new code here that's going to be replaced. It's going to sort of replace the code that I'm evaluating. And that code is actually going to create a new symbol here, let a new symbol, and it's going to evaluate the first item if, I'm going to use this symbol here, if that true symbol is logically true, then in AND, I say, oh, well, that doesn't tell me that it's false. So I'm going to go on to the rest of the thing. And at that point, I recursively call the AND macro on the rest of the items. Otherwise, I'm just going to return the value that we just determined was logically false. So now you know how to write AND in a macro. And if I sort of expand that, in an example, I put AND 1, 2, and 3. So 1, 2, and 3 are all logically true because they're not nil and they're not false. And this expands, if you use the macro expansion utilities, into, it says let I equal 1. If I, which I will be evaluated true, then let the second one, here we're moving on, and then if J, so J is 2, and J will be true, then it tries to evaluate the third item, which is 3, and it gives you back the logical value of the last item. Otherwise J, otherwise I. So that's actually what's happening sort of under the hood. So macros give you the ability to change the order that things get evaluated in and possibly not evaluate them at all. It allows you to read a data structure and then modify that data structure before you do things with it. It does not allow you to modify the syntax of the basic Lisp expressions, so the actual sort of parens and things like that. There's a facility in Lisp called reader macros that actually do let you do that. And sort of there's a very principled reason why Rich didn't allow reader macros, and that's that when you use reader macros, you actually end up creating language that other people can't read unless they have your reader macros. So that means you sort of create this Tower of Babel at that point where everybody has their own very customized dialect. You've created your own language at that point, and nobody can read each other's things. And so I think it's actually, this comes up on the mailing list frequently. Somebody asks, why don't we have this? And somebody will argue passionately for it. And the reason is it means that we can always read someone else's code and evaluate that code. And that means that people can create different languages with different macros that come from different libraries and different people, and you can put those things together and they'll still actually work. So that's actually, I think, is really, really important. The other interesting thing to talk about here is that it's a little hard to see in here, but I'm actually getting, when you get the macro, you actually have access to the full data that is the other arguments that are coming in with the macro. And that is Lisp data. So this is where you get to the notion of homoiconic, a homoiconic language means that your code and your data are the same thing, the same representation. The representation of Clojure code is Clojure data structures. And that means that you can use all those sequence functions on the code that you're about to evaluate before you evaluate it as code. And that means that you can do some pretty interesting and scary things if you want to. So sort of reviewing what we've talked about functions as a way to sort of name and manipulate code, create black box abstractions around functionality. We've talked about collections, which are based on these common set of traits. We've talked about sequences that talk about logical lists of values that are used all over. We've talked about records as a means of making data types. Talk about multi-methods and protocols as a way of getting polymorphism over those types or other things. We've talked about atoms, refs, and agents as a means of abstracting state and the state changes over time. Macros as a way to abstract syntax and order of evaluation. We have not talked about namespaces, which are a way to provide modularity, or metadata, which is sort of a way to attach out-of-band information to data structures. Those I cut out of the talk. I think they're less important, but other very central abstractions in Clojure code. And the thing that I think is really important about this is not just that there is this really important core set of abstractions here, but that they support each other. So you'll see that, like in the state model, it's dependent on having immutable values. So they're sort of backed up by collections and by having the ability to do functions. Polymorphism and functions sort of use the same function dispatching machinery under the hood. Records use the same traits as collections. There's a lot of overlap between all these things. They work together, and I've looked at and used a lot of languages, and I find that languages that have a lot of these interrelated support in between features tend to feel very cohesive when you use them. And that's a sort of a qualitative sort of feel, but not a quantitative one, but it's something that I've seen. So I wanted to give a couple of quick examples. This goes to 5:10. All right, I got 10 more minutes. All right. These are some examples from different Clojure libraries. This is in Cantor, which is a library for doing statistical analysis and charting. And if anybody's heard of the language R, a lot of people use R for statistical modeling. And Cantor actually supports a lot of the same basic kinds of functionality for evaluating functions, working with data sets, charting them. You'll notice here that it's using due to, which is a built-in Clojure thing that applies functions to a value. So function plot here is actually creating data points that represent a function based on a distribution, and then adding into that, I think I just said that right. And then adding into it the LaTeX for the actual function. This is you see you don't have to write much code to do that sort of thing. That's also, and this will actually create the chart for you. And you can actually, there's a view function, which I probably should have put in here, that actually will literally show you the view of the, pop up a swing window at that point that actually has the view in it. There's nothing, you notice this is very idiomatic. In Cantor code, you'll notice that we're calling functions, we're using primitives, we're using core Clojure features. There's no special weirdness here. Ring is a library for writing HTTP handlers. So it's really sort of the base layer for writing web apps. And there's a number of web app libraries that are written sort of over the top of Ring. It represents HTTP requests as a map. So you see the map data come in. It represents responses as a map. An application, a layer in that middleware, is a function that takes a request and returns a map. So that is the model for writing HTTP Ring adapters or apps or whatever. You can nest those, so you can have a function that sort of wraps other functions, and you can create this sort of decorator style of pipeline of requests and responses. It's a very clean model, and there's layers for anything you'd want to do, pretty much. Both Ring and some of the other layers have things like routes, so they match Rails and let you, dispatch on URLs and to find, evaluate a function for a URL and that kind of thing, a URL pattern. Hiccup is one of several templating libraries. This is how you would sort of create HTML. You'll notice that all of the XML tags that end up in HTML are you just show as keywords here, and you nest them together. There's another library called Enlive that does the same kind of thing, but is a bit more powerful. It also allows you to do scraping, so you can scrape HTML or other languages and get them into Clojure data structures. This is all, you notice these are all Clojure data structures here. We're just using Clojure data structure to represent things. It's all vectors and maps and things like that. Cascalog is a really powerful library. I saw a talk on it last year, and it blew my mind what you could do. This is actually a query in Cascalog that actually runs on a Hadoop data set. So this is actually a query language that's based on Datalog, which is kind of the language used by database researchers. It's a very old query language. It predates SQL. Most of SQL stuff is sort of defined in terms of Datalog proofs and things like that. So Cascalog is sort of taking that Datalog syntax and sort of brought it up to allow you to query over Hadoop data sets. This operator here actually defines a query and runs it. So this is actually a special, this is just a symbol defined in Cascalog. There's nothing, not really a lot of constraints on what symbols can have in them. So you can create symbols that look like syntax in a lot of cases. It defines where to put the results. So here we're saying standard out, but you could also tell it a function, a sink, a Hadoop sink, that actually tells it to go put it in a database or do something else with it. It says which variables to actually, which things to project out of the query. And this says, give me all the persons that have an age that equals 25. And the ordering of that is something to talk about separately. So this actually might run over a big distributed query over a whole database or whatever. It's a very simple looking query, and there's a lot of power packed into this abstraction. You can actually put other predicates after this. These first two are kind of important from a position point of view, but after that you can just have a string of predicates, and they all sort of compose together. You're using Clojure to sort of compose these powerful abstractions, these predicates. And this is another example doing similar kind of thing. It's actually getting all the sentences and splitting them based on and producing words. This is another special kind of Cascalog predicate here. and then at the end it's applying an aggregate function that's counting all of those words. So this might actually, you could like, if you had a Hadoop data set that actually was storing like web pages, like the internet, for example, you could run this function, it would give you a word count of the internet. So that may be a silly thing to do, but this is the kind of things you can do with a very simple abstraction. It's just, I think it's really a beautiful use of all the things that are available in Clojure. And to kind of close things out here, I've got a set of slides, and we're going to kind of go off on a little tangent and come back. I ran across this while I was doing some sort of searching for this talk. It's Greenspun's 10th rule of programming. It says that any sufficiently this actually was from 1963 or something like that. So C and Fortran were the other two languages anybody used at that point. So you can assume that's any other language too. So any sufficiently complicated program contains an ad hoc, informally specified, bug-ridden, slow implementation of half of Common Lisp. And that's probably not half wrong. There's also some corollaries, including Common Lisp, which you tend to reinvent these things over and over again. And then a little dig about Prolog here at the end from Norvig, which also is true. And you see there are several people implementing variants of Prolog in Lisp. Jim Dewey in the room here has one. But Prolog has some beautiful ideas in it, so that's why. So that was kind of an that statement. If we go back, any sufficiently complicated blah, blah, blah. And then the corollaries is an example of a snow clone. Going off on a tangent here. And a snow clone is sort of these Mad Lib cliches. So these things that have these keywords, and you recognize the cliche even if you change the words that are inside of it, right? And the word snow clone actually comes out of sort of the canonical version of this. And this is where that term originated. I'm sure you've seen this sort of a phrase about Eskimos have 100 words for snow, and then programmers are supposed to have 100 words for abstraction. That stuff actually comes from the research of Worf and gets back to all this research around what's called linguistic relativity and this notion of does the language that we think with, does that influence, is the language that we have to think with, does that actually influence what we are able to think? And there are lots of people who've explored this idea. You see, like in the book 1984 by George Orwell, he had Newspeak, which they were trying to force a new language on people that would get them to think differently about their government and things like that. So that's one example in literature. There are languages out there that talk in terms of particular the orientation in space or the way they count in logarithmic things, or they don't have past tense. There's some pretty weird languages out there, and people in those cultures don't think in those ways. They don't think in the ways that we do. They don't even have words for those things. So there's both some like strong and weak versions of this. I think at this point, there's been a lot of research on this over the last years, and I think there's pretty good evidence that there are some things that all humans pretty much perceive the same kinds of range of things there, and there are also things where it seems to be pretty flexible, and the culture you're brought up in actually influences what you think. And I'm talking about this because I'm going to make a sort of a corollary there to say, do the abstractions in our programming language determine what we can program? And I'm not really going to answer that question, but it's something to think about as you end for the day. But for me, I've found that I've spent lots and lots of time working in Java, and it's not at all uncommon for me to be in Java and to see some abstraction, some piece of code here and a piece of code here, and they're kind of the same. They're kind of doing the same thing, but the way that they're different is really is either impossible to abstract or it's just really cumbersome to do so. A lot of the design patterns are involved with kind of bringing out that abstraction. And then the downside of some of those design pattern solutions is they actually end up creating more code. So you can make it more abstract, but you also make it much more verbose at that point, and you add a lot more structure around it. In Clojure, I don't feel that as much. I really feel like oftentimes I'll write some code, and it's not very good, but I feel very comfortable coming back later and really taking another look at it and making it more concise, making it more abstract. And if I then come back again later on, I can do it again. And I don't get to an end with that. You get you just basically, it's it's like George Lucas. I'll keep coming back to the well as long as I, and until somebody stops me. So at some point, you just sort of, cut it off and say, I'm going to stop there. It's good enough for now. But I know I can come back later and do some more on it. And I didn't feel like that in Java. So so hopefully you'll give Clojure a look. That's all I got. Are there any questions? Okay, so I'll try to remember those and repeat them. The first one was a question about what Clojure is appropriate for, right? What kind of things you would write in it. And Clojure is and was very explicitly intended to be a general-purpose programming language. It's just like Java or C++. I don't see any constraints on what you can write in it. People have written pretty much anything you can think of. People have written games and enterprise apps and web apps and logic programs and big, just hairy distributed programs and pretty much anything you can think of. Somebody has used Clojure for it already. I think there probably are sweet spots for Clojure versus other languages. I think that there is not an environment that lets you create a web application as easily in Clojure as you would in something like Rails, and supports you as far as like schema migration and all the tooling and the testing and all that doesn't exist in Clojure. There are wonderful, fairly fully fledged web libraries for Clojure, and people do write web apps in Clojure, but it's not going to support you as much as something like Rails or Grails or something like that, or Spring. Yeah. So it depends what you mean by that, but I might disagree with that one. And then you also asked whether you would normally call this from Java and leave some of your logic in Java. I don't know. We're writing completely in Clojure. So we have some web apps. We have command line tools. We have big, hairy servers and clients and a lot of different kinds of things. They're all written in Clojure. You certainly could. There are ways with Grails to call out to Clojure controllers. So that's a path that has been burned pretty well. And there are people like, I know like Bank Simple is using both Clojure and Scala for different parts of their application, so they're marrying the two of those together. There are a lot of people that use Ruby or use Ruby for the front end code and then Clojure for the back end services. So there are people that do that. But I understand, like, if you haven't ever done functional programming or Clojure or something like that, and I felt this way a year ago. Like, I wasn't quite sure how to start going about like structuring my program, but it turns out that it's really not that hard, and once you get started with it, it feels very natural, and it's not. It's just different. It's not more or less able to support a full application. So, yeah. So the question is how important a Java background is, and Jim has a comment. I'm going to make a comment first. I would say that that I have a really strong Java background, and there are a number of times when it was really easy for me to guess what Clojure was, how Clojure was implemented, and what it was doing under the hood, and reason from that about what it was doing. You also know all of the JDK is available to you because Clojure has excellent Java interop. You can call Java methods, Java can call you, you can subclass, you can implement interfaces, you can do all of those things. All those things are available. So if you know the JDK really well, you can dip down into it and use things like the Java util concurrent facilities if you really want to, and things like that. I don't think you have to have it, but I found it beneficial. So.
I'm the exact opposite. I have never done with Java, and I still love Java, and I love Clojure. Now, what he did say about knowing the JDK is great.
Yeah, the JDK has gotten pretty large, so that's a daunting thing to try to learn. In addition to the Clojure API, which itself is pretty large. I showed you that sequence library. That's just a subset of what's available. And it's very frequent that me or one of my colleagues will be writing a function and we'll be gnashing our head against this problem. and then you get to the end of it, and you ask somebody, you say, hey, how's this look? And they're like, oh, yeah, that's in the core API, or that's in the contrib APIs, or whatever. And like, why did I spend all that time doing that? So it's really hard to sort of get your head around everything that's out there. There are better and better documentation sources for that every day. But, yeah. Yeah, there's some, Clojure is not as fast as Java. It actually, because most of the, performance is a really important consideration for Clojure, and it's something that Rich is constantly working on improving. And in most cases, it's not something that has been an issue. It has some, definitely, you're creating a lot more classes and a lot more garbage. So you will tend to work your garbage collector more than you would with the equivalent Java program. I haven't seen that be a problem yet, but I have read things about people and needing to do more of that tuning. You're also creating classes which end up in permgen, which can be a problem in Java. If anybody's done JVM tuning type stuff, there is some really useful work going on for the Oracle JDK right now, where they're planning on getting rid of permgen. So that would be much to the delight of dynamic language authors on the JVM, not just Clojure, but also JRuby and other languages. So in most cases, it will try to get to the point where it's actually making a direct method call to a Java object. And in that case, it's identical. If you're using dynamic dispatching features, then that has to go through some code that does the dispatch. So that adds overhead. There are lots of ways to make that, to optimize that, and Hotspot will do all sorts of things. Inlining, once you get to a certain point, it will help you out. But there is still some overhead there that you can't get rid of. Records and protocols were both partially added because they provided higher performance implementations of data types and polymorphism. So those were benefits of both of those. Anything else? Type safety, it's dynamically typed, so it's unsafe. It won't crash. It'll just give you the wrong answer. So you can provide type hints, and those are used as hints. They're not required. They're not enforced, but they are used to pick the right Java method more ahead of time and avoid some possible Java reflection. So you can add those, and there's actually a pretty small set of cases where you actually need to supply hints. The type inference into things like Java and stuff is actually really, really good. And it's only, the cases where I have run into cases where it matters, there's a warning flag you can turn on that will tell you, I'm using reflection right now. And it'll tell you, I'm using reflection at this function, and I don't know what type this thing is. And then you can say, oh, I know what that is. It's always a string. And you put a string hint there, and then that warning goes away, and your code gets 10 times faster. So, and I have run into that once or twice. But it's usually pretty narrow, those cases.
What's the Clojure community like?
Clojure community is a ringer from the back of the room, I think. But the Clojure community is great. There's a wonderful mailing list, very helpful, friendly people on it. There's a great IRC channel, which always has 100 people in it. And almost always, if you pop up on there and ask a question, somebody will point out that the error of your ways, or compliment you, or whatever you need at that point in time. There's a company called Clojure Core, which is sort of backing the development of the language. That includes Rich Hickey, who created the language. It also includes a number of people from Relevance LLC, and that's sort of the group that sort of is in charge of the language more than anything else. There is a pretty open contributors list, so I'm a contributor. I've contributed patches to Clojure and had them accepted, and test cases and things like that. And if you want to get involved, there's plenty of opportunities. It's still a very young language. There's a lot of the next version will have a bunch of changes around things like dealing with primitive numbers and getting primitive numbers to work in more cases and more transparently than they do now. I haven't run into that as a problem to date, but it's one of those things that is just it's finding the right path through it that balances the need for speed with primitives and not wanting to put too much of that stuff into the language and abstract yourself from the JVM